Let's talk about power functions. So the definition is in the textbook. In general, it's a f of x is equal to k times x to the p, where k and p are real numbers. So real numbers are anything as long as there's not an I involved. So 1, 7, negative 2/3, 5/6, square root of 2 pi. Those are all real numbers. So some examples of power functions are y is equal to 3x to the fifth, k is 3, p is 5, y is equal to x to the 1/2, k is 1, p is 1/2, and y is equal to negative 14x to the negative 2, k is negative 14, e is equal to negative 2. The ones that I want to focus on in this video are ones that look like y is equal to x, y is equal to x squared, y is equal to x cubed. Keep going. So I'm going to go with positive integers for my exponent. The reason for that is I want to figure out the end behavior of these types of power functions. End behavior means if you're talking about the graph of this, what's happening way out to the right for really large x values and way out to the left for really large negative x values. So we know the graph of quite a few of these so far. So we know y is equal to x. Looks like the following. We know y is equal to x squared. Looks like a parabola. And we know y is equal to x cubed. Looks like this. Okay, so the cool thing is if you kept this pattern going, y is equal to x to the fourth looks similar to x squared. They are different, but they're similar in the sense that their end behavior is doing the same thing. They're both up, up. And the reason for that is if you take, say, a really big x value, say 10,000, that's pretty big, and you raise 10,000 to the fourth power, well, that's a really big positive number, which is why in the end that graph goes upright, just like y equals x squared went upright. If you plug in a negative, big negative, like negative 10,000, and you raise that to the fourth power, well, negative 10,000 times itself 4 times is going to end up positive because there's an even amount of negatives. Negative 1 times a negative 1 is a positive 1. And another negative 1 times another negative 1 is another positive 1. So this is going to be positive in the end. So 10,000 to the fourth is really what you get, which is also why on that left side it goes up, left, just like x squared. So the same type of thing is going to happen anytime you have that even exponent, like x to the sixth, x to the eighth. They're all going to be up, up. Versus these odd ones, say for example, if you evaluate 10,000 over here, take 10,000 to the third, well, that's positive. It's a really big positive number, but it's still positive, so you're going to be up, right. Versus if you had plugged in a negative, here's where it's different. Negative, set it, should probably write it, there we go. You'll get a negative 10,000 to the third. Well, a negative 10,000 times itself 3 times is going to be a negative overall, which is why it goes down left, because the y value is negative, and it's big negative, okay? So any odd exponent, like x to the fifth, x to the seventh, is going to have that same type of idea. If you then added, say, a negative out front, as in like, if you wanted to graph a negative x cubed, well, that negative is outside, so you're going to flip the y value, so it ends up like this. So the end behavior switches if you have a negative out front, similar with if you had, say, a negative x to the fourth, that negative is outside, so you're going to flip it down over here and the end behavior switches. So there's two things that the end behavior of these power functions that we want to focus on depend on, and that's whether n is odd, sorry about that, or n is even. So let's go with n is even here, n is odd over there. Okay, and then if our coefficient up front, let's call it k, like we already did, if k is positive and k is negative. So here's my little table for what they're going to look like. And again, I'm focusing on things that are like y is equal to k times x to the n, where n are things like 1, 2, 3, etc., and k is real. Well, if they're even, then things are going to act like x squared, which we know what x squared looks like. If it's just x squared and you got a positive number up front, it's going to look like the following. The squiggle in the middle just means I don't know what's happening in the middle of that function. I'm just focusing on end behavior, so it's going to be up, up. If you multiply outside by a negative, then it's going to flip to down, down. If you're talking about an odd one, that's like our x cubed. So if you think about x cubed, we know what that one looks like. Its end behavior is down, up. And if you add a negative up front, it's going to be up, down. Okay, let's do some examples. we find the end behavior of the following function. So let's start with, let's go with y is equal to a negative 5x cubed. Well, cubed is odd. K is negative 5, which is negative. So if I get this table back in, it looks like I'm over here in this bottom right corner of the table. So that's up, down. Okay, well, that's how you draw it. If you want to write it out more formally, if you write as x approaches negative infinity. So negative values of x are out left. So as x approaches negative infinity, the y values are going up. So that means y approaches infinity. If you want to talk about x approaching positive infinity, that's asking about the right side behavior. Well, that's going down over there. So y's are approaching negative infinity. Okay. How about, let's go with y is equal to about 3x to the 18th. 18 is even, 3 is positive, so the end behavior is going to be just like x squared, which is an up, up. So for the left end behavior, we got x approaches negative infinity, y is approaching positive infinity because it's going up, and right end behavior, as x approaches positive infinity, y is also going up, so that's positive infinity. Okay, how about one more? Let's go with y is equal to a negative 6 times x to the 14th. Well, x to the 14th. 14 is even. Negative 6, we'll flip it down, so it's going to look like the following. Left end behavior. So as x approaches negative infinity, we have the y's are going down, so y is approaching negative infinity. And as x approaches positive infinity, right end behavior, that means y is going down, which is negative infinity.